Artificial satellites are man-made devices or machines man-made devices or machines revolve around the Earth, around the Earth. Now, artificial satellites are used for different things like uh, uses in general, remote sensing, that is to study about the surface of Earth or the clouds, remote sensing, weather forecasting, weather forecast, weather forecast, or communication. Now, we'll describe two kinds of satellites. There are many kinds. We are discussing only two kinds of satellites. So we'll have types of satellites. They're entirely different when it concerns about their orbits, types of satellites. Now you have two kinds of satellites that we are going to discuss here because of the nature of their orbits. The two kinds are, the first one are polar satellites. And the second type is geostationary or geosynchronous satellites. Geostationary satellites, they are also known as geosynchronous or geosynchronous satellites. So geostationary satellites and geosynchronous satellites are the same kind of satellites, but with different names sometimes. So we'll start with polar satellites. We'll start with, let's say, polar satellites. One, polar satellites. Now these satellites, they passes over the poles. These satellites have orbits passing over both the poles. And apart from that, these are generally low altitude satellites, and they are typically used for remote sensing and studying about the surface of Earth. So are used for remote sensing, weather forecasting sometimes, remote sensing spy, this kind of work, and they travel around Earth in every 1 hour. So the time, the orbital frequency of the orbital, right, which comes around, let's say, 1 hour, 100 minutes or so. The period of revolution is of the order of, let's say, 100 minutes. It means that on the same day they will be passing over the same terrain several times. So it's called sometimes they are called sun synchronous orbits. They are often deployed on sun sun synchronous orbits. What does it mean by sun synchronous orbit? It means that they come to the same place, about the same place over the Earth, with the same lighting conditions. So every time they come over there, the lighting conditions will be exactly the same. So they scan the regions on the same lighting condition or light condition. So it's easy to compare the images. That's the idea. So this is basically for surveillance studies of the surface, that kind of a thing. This is generally the idea of polar satellites. Now, these are near orbits. Solar satellites are really polar satellites are orbiting close to the surface of Earth. So they usually orbit close to the surface of Earth. So let us try to work out the details in case of polar satellites. Orbital description, we'll just have it, do it in a different color. Orbital properties of near Earth satellites or low orbit, low altitude satellites. So let us work out the orbital speed, and then let us work out the orbital frequency of revolution and this kind of thing. So let us work out the orbital velocity. Orbital speed. And now in this case, In this case, the radius of the orbit radius of few hundred kilometers. So we can assume in this case radius of orbit r is equals to r is the radius of Earth plus h, that is the surface of the Earth, height from the surface of Earth. But in this case, near Earth orbit, h is much smaller than r. So we can just assume that r is approximately equal to the radius of Earth. That radius of Earth comes around 6.4. This is approximate value, 10 to the power 6 meters. Because compared to the radius of Earth, the height of the satellite from the surface will be very little. So it will not make any significant difference. The mass of the Earth has a value approximately, let's say 6.0 times 10 to the power 24 kilogram. Of course, the gravitational constant G is equals to, we know the value of that, 6.67 times 10 to the power minus 11. So we use all these values, we can actually work out the orbital speed. Then the orbital speed V is equals to, we already know the equation, square root G M. Here we have to write the orbital radius, which is more or less the same as the radius of the Earth. So we can write this. So you can write the value here like this, under root. G has a value 6.67 times 10 to the power minus 11. And obviously the mass, you can write the mass of the Earth. The mass of the Earth is 6 times 10 to the power 24. And then you have the radius of the Earth, that is 6.4 times 10 to the power 6 meter. When you work this out, the value you get is approximately, the speed is equal to, approximate value when you work it out, is the V is equal to 7908. What I got calculating the value, meter per second. Or you can just write approximately 8 kilometer per second. This is the tangential speed of the near Earth orbit satellites. We can also find the omega value, angular speed. Let's do it in a different color. All right, here we go. Angular speed. We have the expression for angular speed. Omega is equals to V upon R. We know that. Angular speed, omega is equal to V over the radius of the orbit, which is approximately equal to the radius of the Earth. So we can just write the expression 7908 meters divided by radius of the Earth is 6.4 times 10 to the power 6. When I worked this out, I got the value 0.002. 0, 0, 1, 2. The unit will be radians per second. Now let us work out the time period. Okay? The period of revolution of polar orbits. Period of revolution of satellites in polar orbits. Let's try to work it out. So you have the expression T is equals to 2 pi over omega, that is equals to 2 pi over omega value we already know, 0.0012. When you work it out, you get the time value approximately 5236. That is 5236. Yeah, it comes 36 in calculation. Seconds, which is approximately 87 minutes in this case. This is the time. This is the time. Now we can calculate the number of revolutions per day. That's also we can calculate. We'll have number of revolutions, per day. Per day in this case means per 24 hours. So let us work out the number of revolutions in 24 hours. Each revolution approximately takes 87 minutes. So we can write N is equal to, let us see, the total time for a day is 86400 seconds divided by 1 revolution takes 5236. 5236 seconds. So this is approximately, it's about 16 revolutions per day. So these are the details you can obtain about near Earth orbit satellites. Now let us go to geostationary orbits. So let's talk about geostationary orbits. Geostationary or geostationary orbits. So satellites in geostationary orbits are typically used for communication because they will always be at the same spot in the sky when looked from Earth. So they appear, this is the main thing. They revolve in orbits parallel to the equator. Parallel to the equator. And the second important thing, they follow the direction of rotation of the Earth. That means they orbit from west to is following the rotation of the Earth about its axis. Now, this makes it, they have the same angular frequency, have same angular velocity as the rotation of Earth about its axis, as the rotation of Earth about the axis. So that means it completes one revolution in 24 hours. It means that T is equals to 24 hours, that is equals to 86400 seconds. Now, when you look from there, they always appear at the same point in the sky. When viewed from Earth, they appear at the same spot in the sky. So they follow the path or the motion of the Earth about its axis. So this is why they're used for satellite communication. So let us try to work out the radius of the geostationary orbits. Okay. Radius of geostationary orbits. I have calculated it already, so I put the numbers in here, and then I'll just write the value I got in this case. So we can write, we have this relationship. T square is equals to 4 pi square over gm times r cube. From this relationship, we can calculate r, that is the cube root of, what will be that, gmt square, gmt square, so gmt square, this is t over 4 pi square. So let us substitute the values. So we get, sorry, that's right. R is equal to, R is equal to cube root of, let's put the values in here. This is the cube root. G value is 6.67 times 10 to the power minus 11. And M value is 6 times 10 to the power 24 kilogram. T square is 86400 squared. Then in the denominator we have 4 pi square. When I work this out, I got a value, the R value I got, this will be in meters. I converted that in kilometers. When I worked it out, it comes around 4 4.23 4.23 times 10 to the power 7 meter. This is the value I got. Close to the, you can write 42,000 kilometers. This comes around 42,000 approximately. This is the approximate value. 42,000 kilometers. This is the height. This is the orbital radius. So for a geostation approximate value. Let's also work out the orbital velocity. So if you work out the orbital velocity, different color here. I'll leave it for you to calculate it probably. Different color I should use. Orbital speed. Orbital speed. Again, we may use the expression Gm over R orbital speed. Yeah, same equations we can use. We can use V is equal to square root of Gm over R. So we need to put the values in here. This is equal to square root of G value is 6.67 times 10 to the power minus 11. M value is 6 times 10 to the power 24. And R value is approximately, you can write 4.23 times 10 to the power 7 meter. When you work this out, what I got here, the V is equal to 2.7 kilometer per second. Usually this is approximately 3 kilometer per second. That is the orbital speed in geostationary orbits.